Hello everyone, welcome to today's program. And our speaker is Dr. Biwei Dai. And Biwei obtained his bachelor degree from Peking University and his PhD degree from University. He's expert in machine learning and its application in astrophysics and cosmology. I think today he will give an interesting talk about the generative model. So let's go.
Thanks for the introduction. So today I'm going to talk about generative models for astrophysical inference. And most of the work is done with my advisor, Ursh, and some other collaborators, Neil, Tony, David, Xiangchong, Rachel, Paco. So I want to start with a very broad introduction about inverse problems. So when we observe the universe, we rarely see things directly. We see the projections, we see the convolutions or integrals of some physical quantities. And in most cases, our goal is to try to infer this underlying physical reality from the incomplete or indirect data. So to give you some examples, here I'm showing the gravitational lensing. Here we are trying to given all these distorted galaxies, we are trying to infer the matter distribution in the lens plane. And another example is from the HT image reconstruction. So in the interferometry, what we are really observing is this is the Fourier mode of the original image. And here showing their observed data in the Fourier plane, and using this data, we're trying to reconstruct the original image. And another more broad family of example is the model parameter inference. Here's an example in cosmological inference. We are observing the large-scale structure as traced by the galaxies, and we try to infer the cosmological parameters from this 3D or 2D galaxy distribution. So, Jimmy once complained to me that every simulation-based inference talk he went to, he would always see a Bayes theorem at the beginning. So this talk is not an exception.
But it's not at the beginning.
Right, I mean, it's the second slide, but yeah. I mean, unfortunately, this is probably the only equation I know how to write down. So I really need to show it at the beginning. So basically, we can view this problem with the Bayes from the Bayesian view. We write down the Bayes theorem. Y here is the physical quantity we try to infer, and X is observed data. And once we have the posterior, we can either get a map point estimator or sample the full posterior. So we usually approximate all these prior and likelihood functions with Gaussian or uniform distribution or other analytical functions. But these approximations may not be accurate in many applications. And also, as we get better and better data, we start to see some non-Gaussianity, and this approximation may not hold. So in many cases, we don't really know how to write down these probability distributions, but we know how to simulate the data, at least approximately. So for example, in the image reconstruction from the interferometry example, we don't know what is the prior of all the black hole images, but we know how to simulate all these black hole images. In the large-scale structure inference, we know how to write down the prior. The prior is just some uniform prior on the cosmological parameters. But here, the likelihood function is more complicated. If you do the two-point analysis, you can approximate that with the Gaussian. But with non-Gaussian statistics or the field level analysis, your likelihood function is really a very high-dimensional non-Gaussian distribution. And we don't know really how to write it down, but we can simulate the large structure. So in this talk, I'm going to talk about we can use generative models to learn the distribution of the likelihood and the prior from the simulation data or some analytical model, and use this learned distribution to solve the inverse problem. So this would be the basic idea of this talk. And I'm going to show you two examples, one on the likelihood, one on the prior. So before going to the applications, I have a very, this is only one slide, very brief introduction of the generative models. So essentially, you can just view generative models as just a parameterized high-dimensional probability distribution. So these kind of models, they try to infer or learn the probability distribution of some given training data. So normally this is done by building a parameterized distribution, p theta of x, where theta is your parameters, and you try to optimize theta to make this distribution as close to the true distribution as possible. So imagine in the simplest case, you have a Gaussian probability distribution. Theta is just a Gaussian, so theta is your mean and covariance. You fit the mean and covariance to yourself. That's the simple case. But the generative model allows you to go to more non-Gaussian and higher dimensional cases. Once you train, you can sample from this distribution and also evaluate the density and use them in the Bayes theorem. So there are many different types of generative models. I won't go into the details of any of them. Just want to briefly mention that, for example, we have normalizing flows. So most of the applications I'm showing today is actually based on normalizing flows. It's just essentially a one-to-one mapping between your parameterized distribution and the Gaussian standard normal distribution. So we have X, your data follows from some complicated distribution. You have a normalizing flow transformation F, map that to a standard normal distribution. And this mapping is bijective, it's differentiable. So once you build such a mapping, you can evaluate the density using this Tyndall variable formula. The density is given by the density of your latent or the Gaussian variable times the Jacobian determinant of this coordinate transformation. Another family of generative models are diffusion models. So these kind of models, instead of learning this or parameterizing this density itself, it tries to parameterize the gradient of the log density. So the advantage here is that when you parameterize the density itself, you always want to make sure it's normalized. But when you try to approximate the gradient, you don't need to worry about normalization anymore. So it allows you to use much more flexible neural network architectures. And yeah, that's the main advantage. And of course, there are many other more. So here I'm just showing some images generated by the diffusion models. So they look, this is very high resolution and they look pretty realistic. And this is actually work 3 years ago. So nowadays, the generative models are very powerful. You can use it for generate images, to generate movies, or to help you write your paper. So yeah, many applications. So but the bottom line, but the takeaway here is that the generative models, they are just a high dimensional probability distribution, and you can use that to fit the data. So I just want to briefly compare this approach to the more like traditional ML approach or supervised way, where you just learn a neural network, which is sometimes viewed as a black box that takes in this input data, the large structure, and magically give you the cosmological parameters. So here I'm just showing some comparisons between these two approaches. With the traditional or the supervised way, it's very easy to train, and the results you can prove, the result will converge to the map using some certain loss functions. But of course, with this approach, you don't really get uncertainty quantification. Also, when your simulation is wrong, you sometimes get biased results. And also, you need to retrain it when you have a new data point. So that is not very convenient. And with this more probabilistic or Bayesian way, you get uncertainty quantification. You can also do anomaly detection, which means you can quantify how consistent your simulation is with the observation. I'm going to talk about more later. And you can also adapt it for different observations. And of course, but all of this comes at the cost of the model becomes harder and slower to train or evaluate. So that's just a very brief background. And next, I'm going to show you two applications. The first one is in cosmology, where we learn the likelihood function, and we use that for the weak linear analysis. And the second example is on image reconstruction from the interferometry. We use that to learn the prior of our image and for the Bayesian inference. Okay, so I'm going to quickly go over these introductions. But here, basically, I'm showing the large-scale structure of our universe. And we see it's highly non-Gaussian and it encodes very useful information about our universe. There are lots of physics we can do with them. But we cannot directly observe dark matter, but we can probe dark matter or the large-scale structure with this with their gravitational effect. And so one example is the weak gravitational lensing. The idea is the background galaxies, their light would be disturbed or distorted by the foreground large-scale structure, its gravitational effect, and then our perceived galaxy shapes would be distorted. And then by measuring the coherent pattern of galaxy shapes, we can extract useful physical information. So many weak lensing surveys on the way or in the very near future. So here I just list some of them. As you can see, they are finished collecting the data. Euclid, we see some preliminary results. I mean, not on weak lensing, but on other on strong lensing and other applications. Rubin probably will start collecting the data later this year, and then Roman is also in the near future. So all of these surveys will measure billions of galaxies, allowing us to constrain cosmology really well. So for the data analysis, the traditional analysis based on the two-point correlation or the summary statistics, it will firstly compress the data into some low-dimensional statistics. Here I'm showing the power spectrum, and then you define some Gaussian likelihood on the statistics, and then you run the MCMC and get the posterior. But of course, you start to lose information if your data is highly non-Gaussian. So I'm going to talk about the field level inference. So the idea is we directly go from the these high dimensional non-Gaussian fields directly go to the cosmological inference. The issue here is we don't have a tractable field level likelihood function of x given y, where x here would be the pixel value of this field, right? That's why it's called field level. So here we'll try to estimate this likelihood function from the generative model from simulations. So how does it work exactly? We start from some cosmological parameters data. We run simulations, the yellow box, we get mock data, x. Here x is just the pixel values of the fields that we will observe. And we give all this x and theta to this green box, which is our generative model. We will try to infer this probability distribution P of x given theta. We use that as our likelihood function for the inverse. So this framework is really powerful, but there are some potential issues like the simulations may not be accurate. So there could be some distribution shifts between your training data and observation. And also this green box is kind of like a black box, so it lacks interpretability. So and I'm going to show you later. The generative model gives you some pretty nice properties that allows you to at least alleviate some of these issues. So how does this field level analysis work in practice? So here I'm just showing, okay, this is still on, this is not really observable, but instead on the dark matter, on some two-dimensional dark matter density field from simulations. here, our likelihood function is given by the normalizing flow, and you use that to infer the posterior. And here I'm showing the posterior constraints on omega m and sigma 8. So the orange color is the power spectrum, the traditional 2-pi analysis. Green one is our field level inference. It's a huge improvement that's also quantified by the figure of merit, which is defined as the inverse of area of the 1 sigma contour. So the larger number, the better. You see, we're getting much more information compared to just using the 2 points information. So that is on the 2D dark matter density field. How about on some mock weak lensing data? Here I'm showing you the constraining power as quantified by the figure of merit for different statistics. Here we have power spectrum and also the non-Gaussian statistics, peak count, CNN, and scattering transform, rather by Sihao here. We'll also show you 3 different survey scenarios, corresponds to different noise levels. And we see the non-Gaussian statistics give you significantly more information compared to the 2-point statistics. But if you go to the field level, you can actually gain even more. Here I show you 2 different these 2 different columns. They are actually correspond. Both of them are field level, but they actually use very different architectures and methods. But we see that they actually kind of converges on the constraining power, which potentially is suggesting that we may have already extracted the full information from the data.
So what can you say about potential systematic issues? So surely the credible reconstraint, your figure of merit goes up, but if it shrinks towards the wrong region, then you could have maybe a very significant deviation from the truth.
Exactly, that's the next slide. Yes. So how the question, the question is, how do we know we can trust our analysis? What if the simulation is wrong and our analysis is biased? So here I showed an example taken from the CAMOS collaboration. Here they are just training some simulation-based inference model on some baryon maps. So on the left column, they are trying to infer omega m and sigma 8. They train their model on TNG simulation, also apply it to the TNG. The model works perfectly. But if you apply it to a different hydrogen simulation, your constraints is everywhere because of this inconsistency between different simulations. So yeah, of course, we need to improve our modeling. We need to marginalize over different baryon parameters, different baryon models, different simulations. But we also need tests to verify the reliability of the analysis. We need to know when we can trust our analysis and when not to. Yes.
Can you go back to the previous slide, the one before this?
Yes.
So when you plot the constraining power,
Mhm.
what is the figure of merit here?
Oh, right. Sorry. The figure of merit is defined on the omega m and sigma 8 plane. It's just the inverse of the area of the 1 sigma contour.
Okay. So I'm gonna ask another question, if that's okay. So strictly speaking, you have Gaussian initial conditions that then evolve in time. And so, ideally, you could reconstruct the early universe field.
Yeah.
So is the increase in the constraining power coming from additional small scale modes that you are recovering? Or is it coming from, is that where it's coming from?
So there are like 2 different ways to do the field level inference. So the way I am working on is more like simulation-based inference, where we learn this marginalized likelihood function, and this likelihood function is marginalized over the initial condition. So I don't really reconstruct the linear density modes. But of course, there are another family of field level inference, which is based on reconstructions. And of course, you can, and that method also gives you the initial. But my likelihood here is marginalized over initial condition. So there's no initial condition in the likelihood.
I guess a similar question is if you go to that contour plot again, like say that you had a truly Gaussian linear density field with the volume kind of equivalent to the volume of whatever the setup is here, how large would the error ellipses be? Are they smaller than the green or are they larger than the green? Because then that's telling you whether all that you're doing is just extracting all of the linear information or if there is cosmological information from nonlinear evolution. And in that case, the
Right,
power spectrum is exact. It has all of the information, right?
Right. Yeah, I haven't compared that, so I'm not sure the answer. I do verify that, for example, in the Gaussian cases, our result converges to the power spectrum, so that's kind of expected. But in terms of this comparison between nonlinear and linear, actually,
Yeah, that's more of a comparison of like information content. Yeah, than whether you converge to the Gaussian, I guess.
I think probably it will be smaller.
Linear one?
Yes.
I would hope so.
If you go to the same small scale.
you mean some information is lost during this non?
Yeah, because physics you expect like in the halo, right? The things collapse into a halo, then you should lose some information.
Yeah, that is my expectation. That's why I was asking if you check that.
Yeah, but I guess for weak lensing, the problem is the projection. So then I know whether that introduces more complexity about how to compare the two situations.
And here your weak lensing is a two-dimensional field.
Yes, two-dimensional.
There's no tomography.
On this example, no. On the current HSE analysis, yes, we have it. Yes. So yeah, we need all these tests to know when we can trust our analysis. So in the standard or traditional two-point analysis, people did all these different kinds of tests, like the goodness of fit test with the chi-square to check how well the model fit the data, the consistency test, making sure that your results is robust to different modeling choices or different scale paths or different redshift bins. And you also do not test to look for potential signal of, potential systematic effects. But all these tests, people are not really, it's not really common to do that for deep learning works. And here I'm just trying to argue that we can do the same kind of test with the generative models, and it will actually give us more stronger or stringent tests compared to two-point. So let me first talk about the goodness of fit test. So imagine you have simulations, you have your observation, they don't quite agree with each other. Let's say you train some traditional ML approach that directly produce or give you the cosmological parameters. In this case, you get biased result because of this mismatch between simulation and observation. And we don't really know it because all we get is just an error bar or some point estimate, and this would be and they would be biased. So if we do the generative approach, all we have is the likelihood function. We can run the MCMC and get the posterior. In this case, it's still biased because we still have the mismatch problem. But one thing we can do is look at the likelihood value and compare this likelihood of your observation with the typical likelihood value of your training simulations. So here's the idea. Imagine you have this 2D data. The green point is your simulation. You fit your likelihood function, which is essentially the density of your training simulation. And if your observation is not really drawn from your training data or training distribution, you expect that its density should be much lower than the typical value of the training data. So this is essentially just a generalized chi-square test. In the two-point analysis or the summary statistic analysis, a larger chi-square would indicate that you have a poor model fit. And the chi-square is essentially the negative log likelihood, right? So here, if you have a small log likelihood, that also indicates a poor model fit. So this really allows us to do the goodness of fit test to improve the reliability. So here we did a simple experiment. We learned the likelihood function of the weak cleansing maps from n-body simulations, dark matter only simulations, so there is no baryonic physics. And we applied this to the maps with baryonic physics included to test whether we can tell this mismatch or inconsistency between the simulation and the test data. So here I'm showing you the ROC curve. So if you don't understand what this plot is, here's a small demo. So the idea is here on the, because this is essentially just a binary classification problem. Right? Given a new data, we want to tell whether it's consistent with the simulation or not. So this plot on the axis is showing the false positive rate of your binary classification. On the axis, on the y-axis is the true positive rate or the completeness of your classification. Right? So imagine you have two distributions. The blue one is training data, the red one is the test data. Now given a new data, you want to tell which distribution is coming from. So essentially you have a boundary, right? If the likelihood false is smaller than the boundary, it's coming from red. It's larger than this boundary is coming from the blue. So for each boundary, you actually have a certain false positive rate and true positive rate that corresponds to a single dot in this plot. And as you move your boundaries, this dot would also move, and that's how you draw a ROC curve. So that's the main idea. So essentially, if your ROC curve is just on the diagonal line, that means these two distributions completely overlap. You cannot really tell the difference. And if it's to the upper left corner, that means better. You can really tell the difference. So here, different colors represent the likelihood from different scales. So the orange one is from larger scales. So you can see that we can, using that, there is no information. I mean, it's the dark matter only maps or the maps without baryonic and with baryonic physics, they are completely degenerate. We can really tell it from the larger scale likelihood. But as you go to smaller and smaller scales, you begin to be able to tell the difference. So which is kind of expected. So we also compare this with the summary statistics. So this work is led by Kang, who is a grad student at Tsinghua University. So here this is essentially the same test as shown in the previous slides. Here I'm showing you the red and green are the field level approach. The blue one is the scattering transform. The orange one is some convolution neural network learned summary statistics. So I didn't plot the power spectrum, but power spectrum would essentially just be a diagonal line. This is because the field we consider here is very small. What we see is that the scattering transform improves from the traditional two-point analysis by a lot, and then the field level further improves that. So I also want to mention that this CNN is trained by maximizing the cosmological information in the learned statistics and ignores all other information in the data, which may contain useful information to tell the difference between baryonic physics and cosmology.
Sorry, the CNN is just trying to have, like, you have two cosmological parameters, right?
Right, here we have two cosmological.
So in principle, it has no ability to do out of distribution detection, right? Because anyway, you will have a best fit, and it only has those two summary statistics.
No, the CNN learned statistics is actually a pretty high dimensional. It's actually, we try different latent space from 64 to 256.
Oh, okay. So it's not that you only learn
Right.
summary statistics.
Yeah, it's a latent space. It's it's a high dimensional vector, but we maximize the cosmological information in that vector. Yes. Yeah, but this does not mean that CNN is robust to baryonic physics. It can still be biased, by the Bayesian physics, since we have degeneracies. And I also want to mention that now we have this field level likelihood function. It also opens up the possibility of model comparison at the field level. So you can really calculate the Bayes factor at the field level when you have two, for example, two Bayesian physics implementation or two intrinsic alignment models. You can really compare them on the field level. Yes.
I guess when you're saying field level here, it can't truly be at the field level because whatever we observe is like some random realization. You don't know what the initial phases are. Or are you actually, sampling over the initial phases and forward modeling from this distribution of initial phases to get to a final answer? Or are you, for example, comparing like the histogram of the pixel values in the weak lensing map to the one generated by your generative model? And that has all of the information in principle.
I think it is the true field level in the sense that the likelihood you really get from this model is marginalized over the initial condition. So you can view that as some
So I guess that given a data set, whatever you generate from your simulator is going to be completely uncorrelated with that, isn't it?
Yes, yes. You sample random initial conditions in your training data. But what the model learns is not really specific realization, but instead it learns the statistical properties.
Yeah, but I guess so it is learning the distribution.
Yes.
I guess not actually the
Not the realization. I mean, yeah, we can generate lots of new realizations after. Yeah, essentially, your likelihood is marginalized over the latent, the initial condition Z here is. Okay, and we also look at how it scales with the survey area or the resolution. So we consider a very small area, but if you go from 12 to 60 degrees square, you can almost certain tell the difference, right? You can tell whether a given data, whether it contains Bayesian physics or not. So and 60 degree square is not really large, right? So for any realistic survey areas, this would be a very strong and very conservative test to tell whether your simulation is consistent with the observation or not. So another test we've been doing is the multi-scale consistency test. So the idea here is we expect for the cosmological data, different scales are governed by different physics. They have different systematics. They have and different systematics have different scale dependence, right? So if we could separate and compare the information from different scales, we could identify the data, the part of the data that may be contaminated by the systematics. So this is what commonly used in the two-point analysis, but again, in field level or deep learning approaches, it's not that common. So what we do here is we use something called wavelet decomposition. So we recursively apply some low-pass filter and high-pass filter to the data. And finally, we would decompose some map to a sequence of maps which corresponds to information at different scales. And we do the analysis on them separately. So without going into any details, just show you some examples. Here is again, the posterior on some weak lensing maps. Here, different colors represent the information at different scales. We see that they are pretty consistent in this case. Again, all of these are at the field level. But assuming you have some kind of noise miscalibration, here we assume some white noise power spectrum. So that is mostly will contaminate your small scales by a lot. So in this case, the purple color, which corresponds to the smallest scales, would be biased, and you can easily tell from this plot. Let's say you remove the small scale, you recover the unbiased constraints. Okay, I also want to talk about interpretability. So this is the generative model is like a parameterized probability distribution. You can sample from this distribution that gives you samples of new data or with similar properties as your simulations. So we verify that our samples they have pretty consistent summary statistics compared to the simulations. They look pretty realistic. So one thing we can do with these samples is we can use them to answer the question where the information is coming from. Why some cosmological models are ruled out by this analysis. So the idea here is, say you have a weak cleansing map. This would be your observation. You give that to your generative model. You have a likelihood function. You run CMC. You get this sigma 8 constraints. Let's say now it's on the lower end. Now we ask the question why a high sigma 8 cosmology is not consistent by the analysis, is ruled out. So what you can do here is you can regenerate a new data from your generative model, assuming this high sigma 8 cosmology. So there's a trick we can do here to make sure that this new generated data has the same realization as your input weak cleansing map by matching their latent code. So this is essentially what the model thinks the data should look like given this new cosmological model.
How can you do this if you're marginalizing over the initial?
So this is a normal is a bijective mapping between this data and the standard normal distribution. So you can essentially view this latent code as some kind of it encodes the realization information.
Okay, so the initial are part of the model.
Yeah, but when you evaluate the likelihood, this information is not used. It's just a yeah.
So you keep the point in the Gaussian distribution fixed, and you change the sigma.
Yeah, we map this back to the latent space, and we use that same latent code to regenerate new data, assuming a new cosmology. And if you they look pretty similar, but if you take a difference of these two maps, you begin to see this residual field. And this would really help you to visualize where the information is coming from. For example, in this case, all these structures correspond to the halos. And my model would tell me that all these halos from the high sigma cosmology would be too massive and not consistent with the input data. Okay, and finally, I'd like to talk about some current works on HSC analysis. So this currently we are applying the same framework to the HSC weak cleansing survey, which is currently the deepest survey for weak cleansing. It has the highest galaxy number density, which is ideal for this kind of field level analysis, probe the small scales. To do the analysis, we run 100 high resolution retracing and body simulations, and we put lots of efforts into the modeling of systematics. Here I'm just showing the distribution of our simulations on the cosmological models, and this is the source galaxy distribution. You can see 4 tomographic bins. And the HSC year 3 data comes with 6 subfields, which is shown here. This is essentially the footprint. So
simulations have different parameters, but also different phases.
Yes, different phases. And we can also generate, because weak cleansing is a projected map, we can also generate pseudo-random field by like
Rotating.
yeah, exactly, of different directions. So I don't have the results on the real data yet, but this is some results on the on some mock data. So here the orange color is our field level analysis. Green one is the power spectrum. We see improvements on these constraints on both omega m and sigma 8. So this is assuming no baryon effect. If we include the baryonic marginalization, unfortunately, our constraints on S8 degrade a lot by a factor of 2. And this is actually because there's strong degeneracy between the this agent feedback parameters and the S8 parameter. See this degeneracy here. So we're not sure if this corresponds to our implementation of the baryonic physics, because here we parameterize the baryonic physics as a transfer function and subtract the small scale power. But yeah, so we're also thinking about, potentially adding some other baryon constraints from NC type or FRB to help you narrow down the baryonic physics.
In the standard analysis with the power spectrum, there's always this scale cut.
Yes.
People have to do. Here you'll do the same thing by stopping your wavelet somewhere or something like that.
Yes, this would be some scale cut on the real space, or on the wavelet space, yes.
And how does it compare with the power spectrum? Are you cutting more or less the same scales, or you are?
Right, so for this comparison we are using the same scales. So, but this is not the same as the official HSC analysis. The official HSC analysis, they use a more conservative scale. So yeah, this is just on some raw data. For the real data, we definitely need to determine how we are going to do the scale path.
But then, you said there was this way of looking at whether the data was a sample from the.
Exactly, that's
Is
the
this
next
the way
slide.
you're doing? Is this how you're finding your scale cut?
That's what I'm going to talk about. Yes. So, yeah. So yeah. So the question is whether these simulations they are accurate enough, whether they are consistent. So for to start with, we just look at the power spectrum, and we compare that to the HM code 2020, which is a power spectrum emulator based on HaloFit. And we achieve about 1% accuracy between 300 and 4,000. So at even smaller scales, we began to lose power because of we do particle mesh simulations at high ratios, and that lose some power on small scales. But these scales are dominated by shape noise anyway, so they are not really important.
The question about like the intrinsic alignment prescription.
Yeah.
So I guess when you're learning from the full distribution, you're including all of the moments, all the non-Gaussianity. But we know that like the non-Gaussianity in the field coming from intrinsic alignments, if you just adopt an LA, is wrong because you don't have, for example, like quadratic shape dependencies that generate a tree level bispectrum. So that seems like a kind of a big challenge, I guess, to deal with that.
I agree. I mean, all of this systematics. I mean, so this is just the first step. So we adopt the simplest model. We are definitely thinking about, for example, adding some either using the time model at the field level, or there's also a paper last year about using HOD to model the intrinsic alignments, which is probably allowing us to do better than this.
Yeah, but these are always calibrated on like the power spectrum of galaxy shapes, maybe not even the bispectrum, right? So then when you're going to the full distribution.
Yes. If it's really
shield ourselves against that.
Yeah, I mean, if it's really giving us very strong like bias or contaminants, the hope is that we can probably see it by looking at our goodness of fit test, because it will introduce some features that's not consistent with the simulation. Okay, so the goodness of fit test. So this is very preliminary results. I got this from last weekend. But here I'm showing you the distribution of the log likelihood. The y-axis is the PDF, and these different colors. The green color is the likelihood of this XMM subfield. This histogram is from training simulations, and the dotted line is from the observation. The orange color is this gamma 15H, this field, and the purple one is combining these two fields. I haven't really finished all the subfields, so I only have two subfields, but still, even using these two subfields, you can already see that our the observation doesn't really agree with our simulations, which is a really big problem. So to figure out what's going on, we also tried doing this at different redshift bins. So here we have the low redshift bins and the higher redshift bins, and we see that at low redshift bins, the observation is strongly inconsistent with our simulations, right? The likelihood value is smaller than 99.95% of our simulations. While at higher redshifts, our observation and simulation, they seem to agree pretty well.
But what kind of, here you also need to have some scale.
Yes, all of this,
What did you want to
this
address
is
it?
2 argumented, which is
And
pretty
what-
small.
How does that compare with what they would put?
HSC, the 2-point correlation function has 8 argumented scale paths.
Much dark, much
Yes,
more
but-
conservative than.
But I have to say there's a separate HSC work. And that they actually
Aggressive?
Hmm?
You said this is for 2 arguments.
arguments.
That's very
This is
aggressive.
very aggressive,
Right.
yeah, that's why.
Yes. But I have to say there's a HSC work that goes to 0.3 at 2-point functions. And they are arguing that there's no barrier in physics. Everything agrees with anomaly simulations.
And we are made of dark matter.
Yes, exactly. So yeah, I mean, yeah, this is a pretty aggressive scale path. This is at 2 arc-minute. But even at this scale path, the high redshift looks pretty good. And for the low redshifts, of course, this is suggesting maybe some systematics not modeled well, either at low redshifts or maybe at small scales, because the lower redshift proves small scales, or both.
Your simulations are covering, I mean, you have simulations covering this entire redshift range. How are you doing that?
So yeah, we have several boxes and we just stack them.
And your prescriptions for each of for like the IAs and for the baryons in each box, how do they vary with time?
The Bayesian physics has some fiducial, like fixed time redshift variation, which is fitted from some hyper simulation. And IA just assume a power law.
Oh, so for both of these, you basically have some functional formula and you just scale them up and down.
Yes, exactly. Yes. So yeah, it could be, for example, the intrinsic alignment redshift evolution is not modeled correctly, so the low redshift has some issues, or Bayesian physics at small scales, or source clustering, or maybe some systematics. So this is something that we have been trying to figure out. So ideally, we could find some, we could improve our modeling to make our low redshift look better. But if that doesn't happen, probably we are just going to do some more conservative scale paths or redshift paths to remove the inconsistency. I'm going to skip this. And I don't have much time, so I'm just going to quickly go over the second part about intensity interferometry. So Neil visited us last semester, and he already talked about this idea of intensity interferometry. So you know that the regular interferometry just correlating the electric field at different telescopes, and the resolution is given by lambda over b. But you cannot do this VLBI at optical band because you cannot really record the electric field at these frequencies. So what we can do here is using this old idea of intensity interferometer and correlating the photon counts at different telescopes. And then what this measures essentially is your visibility squared, which is basically the amplitude of your forward mode. So you kind of lose the information, but the advantage is that there's no restrictions on baselines. So you could do very long baselines and have much higher resolution compared to the EHT because we are using the optical band. And many applications for this potential idea, including studying agent physics, measuring Hubble constant, or some other astrophysics. But the challenge here is if we want to make the image, we don't have the phase information. So we want to infer the missing phase information from the observed measurement of the amplitude. So this problem is also known as the phase retrieval. This reconstruction problem actually has a very long history. Actually people studying doing this coherent diffraction imaging, they are also measuring the amplitude of Fourier modes on the detector, and they use the amplitude information to try to infer the internal structure of their samples. Their algorithm has been developed in the 1970s and 80s, and even demonstrated in the experiments in 1999. So why is this problem even possible? Because you already lose lots of information. So the answer is you really need all these additional constraints or regularizations to help you retrieve the phases. For example, your pixel value has to be positive. You cannot have a smooth image. The image has to be compact. And there's even a theorem that tells you that this signal can be uniquely reconstructed if the Fourier amplitudes are oversampled by at least a factor of 2, which means for an image, all these boundaries have to be have 0. Right? The pixel value can only be non-zero at the center. You have this very strong compactness regularization. So there are some traditional iterative algorithms. I won't go into the details. Just want to show you that this traditional algorithm works pretty well, assuming a noiseless case. So you start with some random initialization, you do the iterations, and in the end, you reconstruct the image, which looks pretty close to the truth. But the issue here is this kind of old algorithms have very strong assumptions. For example, the compactness, and you also have noiseless data, you fully sample your UV plane, but in reality, our measurements are sparsely sampled. If you remove the number of Fourier modes you measured with this kind of traditional algorithm, you start to get nonsense. And also, when you have noisy measurements, you also the algorithm also perform pretty bad. So again, our solution is to put this in the Bayesian framework. Here, the likelihood would be given by the measurement noise model. And the prior would be learned using generative models from the GRHD simulations. So there are lots of potential choices for the prior. I won't go into the details. So for the experiments, we consider 3 setups. We have the analytical Shapura-Sunyaev disk. We have Li Zhong gave me some of his geometry simulations, and I also took some similar geometry simulations from George. But those simulations are for radiation inhibition, so they are not really for AGN, but for like EHT image black holes. So, but here still we use them just to demonstrate this algorithm. So this is the analytical alpha disk. On the left, we show the truth, and then different samples. We also show the mean of our posterior and the standard deviation. So you see that when you have very low noise and densely sampled UV plane, you get very good reconstructions. And also want to mention that even though the noise level here is not really, is pretty low, but still the traditional algorithm really fail on these examples. If you change the noise levels from top to bottom, here I show examples. Basically, we have higher and higher noise as we go to the bottom panel. And we see that when you have higher and higher noise, your prior kind of become more important. And finally, in the end, you would really just generate random images from your priors because your likelihood contains almost no constraining power. So on the bottom, the number of moles with signal to noise ratio larger than 1 is only 1. So essentially here we are just measuring 1 mole, so which give you nothing. But of course, if you have a higher signal noise, you get better confidence.
The correlation coefficient when you have one node is 0.7. Is that a statement that your prior is very correlated with the output? Or
Yes, because all of the images would have this disk at the central, and yeah, I mean, if you put it everywhere, of course, you will get 0. Or, yes. We also try changing the UV coverage. So here, from the bottom, we observe all the modes, and we decrease the number of modes, and this doesn't have a significant effect on our reconstructed images. Unless we go to 20% of the modes, then we begin to see some effect. And then those are on analytical disk profile, so very smooth. And here we look at how our model will perform on the generative simulations taken from George. And this is just some photon rings. And you can see that we can still reconstruct all these pretty complicated features from the data, assuming pretty high signal to noise ratio and good UV coverage. Okay, so now the question is, what would happen if our prior is wrong? What if our simulation is wrong? We have a misspecified prior. What would happen? So here I'm showing an example where our prior coming from some analytical model is given by the alpha disk with added some analytical spiral arm and also add some turbulence, which is modeled as a Gaussian random field with some given with power law, power spectrum, and then the index is marginalized. So some typical images of our prior looks like that. Everything is analytical, and we apply that to generative simulations from Li Zhong. So these are for AGN disk. So here is the result. On the left, we have the truth, and here we show different posterior samples, posterior mean, standard deviation. So I think we are also doing pretty well here. So for this case, this is very unique case because here I think the black hole has very weak jet. So there are lots of gas above the AGN disk, and that's why you cannot really see the disk. All you see is all the gas that's on the surface of the disk. And even in this case, we still get some non-disk structures, which is really does not really look like our prior. Another example we did is we train our simulation on the photon ring generative simulation from George and use that to reconstruct the smooth alpha disk model. So here the truth is shown on the upper right. We show different noise levels, and we see that for very high signal noise measurement, our reconstructed image is pretty smooth. But as you go to higher and higher noise, you begin to get all these features, which is coming from the prior. But still, if you average over all these images, because all these spiral arms, they are just randomly drawn from the prior. So they are actually, if you take a mean of them, they actually average to 0. So you get some pretty smooth image in the end. This is just another fun example where people doing EHT observation, they try different priors like human faces or cars and cats, and they use that to reconstruct the images. So I talked about this in the coffee before, so I'll just skip this. And sorry, I take too much time.
Any question from the audience? I have a question here. You are training your like model for EHT, you are training it with simulation. So what if like here you already know the ground truth, but what if in your observation you don't know the ground truth?
We know the ground truth, but the ground truth,
I mean, if you supply with your model with unseen data, here you already know like the answer about the.
right here, this is already unseen data. I mean, the truth here is analytical disk, and the training data is like photon ring simulations, so they are very different. The model has not seen a smooth analytical disk before, right? So this is already.
Just following up on this question, like in this case, can you tell to some extent how your model or how the predicted thing deviate, or like some like before you can tell like how much your simulation is different from observation in this case, can you?
Yeah, here we can, of course, yeah, we can also do a similar test. We can see how well our guaranteed simulations agree with the observation using the same Green-out fit test that I mentioned in the first part. I didn't show that, but yeah, we are thinking about doing that for UHT. Yes.
Questions? Okay, let's thanks Biwei again.